Okay, I'm going to show you how to use a chi-square critical value table to evaluate your chi-square statistic. So we're looking at a critical value table here. I'm going to write all over this, and if you have a copy, you can write on yours as well, or if you want to come back and make some notes or print a copy and come back and make notes on your copy. So some things you need to know. First, this column here is degrees of freedom, and the degrees of freedom are the number of categories in your data set minus 1. So our data set is these 3 genotypes, right? Each student can be categorized as either plus plus, plus minus, or minus minus. So the degrees of freedom in our experiment is 2. Your experiments vary, depends on what your categorical or dependent variable is, how many categories you have. But degrees of freedom is number of categories minus 1. So we're going to compare our calculated value, or chi-square statistic, to this table. And remember, our value was 2.7. So it falls between this number 1.3 and 4.6. So what that tells us is we have to go up to the top here and get a p-value, which is what this top column is, which for our purposes is essentially the equivalent to the probability of error. It's not exactly right, but it's close enough for our purposes. So we're at between 0.5 and 0.1, which is 50% or 10% likelihood of error. So typically we want to look at a p-value of 0.05 or smaller to think that the difference between two data sets is meaningful. So the 0.05 value is kind of our minimum standard. So you can put a line here and say if your chi-square statistic or calculated value is on the left side of this line, then your error is high. The meaningfulness is low, and so the difference is not meaningful. And this basically says that the two data sets are essentially equivalent. So your observed value essentially matches your expected value, and any difference between them is due to chance. And so in this case, you would reject your null hypothesis. Reject your alternative hypothesis, which is the one that says that the differences are meaningful, and you would support your null hypothesis. So if your p-value is on this side of the line, you can support the null hypothesis, reject the alternative hypothesis. On the other hand, if you had a really high calculated value from your chi-square test, say it was over here at 13, then that would say there's a really big difference between these two data sets, and the likelihood of error is very low, 0.1% error, probability of error is 0.1%, or you could also say you're 99.9% confident that these two data sets don't match each other, that there's very low probability that you would get this result by chance. So this is not due to chance, and the likelihood that it's due to chance decreases as you go to the right. Low error. Difference is meaningful. Your null hypothesis is rejected because your observed does not match your expected value. So the two data sets don't match each other, and you can reject your null hypothesis. So this supports the alternative hypothesis. And the higher the calculated value or lower your p-value is, the more confident you are that it's not due to chance because your error is lower. So for our result here, our p-value we would report as less than 0.5. If you had this calculated chi-square statistic of 2.7, p is less than 0.5, or the error is between 10% and 50% error, like I said. So this is a not significant difference between these two data sets.